Right, so taking a look at doing some electron counting. So the first thing you need to do for electron counting is to figure out what type of ligands we have. And that'll tell us what oxidation state we have of rhodium. So if we look to figure out what type of ligands we have, we need to pull these ligands off of the rhodium and see if they would have a negative charge. So we pulled this off, right? This circle means it's aromatic. So we pulled this off, right? This is a 1, 2, 3, 4, 5, 6 membered ring. If I pulled this off, that wouldn't have a negative charge. That would just be a benzene ring. All right, so that's not an anionic ligand then. But what about this 5-membered ring? Now for this, right, again, circle, that means it's aromatic. For this to be aromatic, this would have to be cyclopentadienyl anion, right? Because for it to be aromatic, right, it needs to be cyclic and have an odd number of pairs of electrons. So it has to have a negative charge there for another lone pair. So this is an anionic ligand. Even though it looks very similar to this, but a 1, 2, 3, 4, 5-member ring means this ligand's anionic, right? So anionic, which means it oxidizes the rhodium. Whereas this is just essentially a dative. Now, that has to do with the oxidation state. It's not telling us how many electrons it's adding or donating yet at all. We're not doing that. Right, all we're doing is figuring out right now, is it oxidizing, is it anionic, dative, or coordinating? Right, if it's anionic, that means it's oxidizing the metal. If I were to pull the chlorine off, right, what would I have? I would have a Cl minus. So that must be oxidizing the metal too. Right, so this is also an anionic ligand. What if I took the ethanol off? I would have this. Does that have a negative charge? No. So this is just a coordinating ligand. Right? The weird part is we don't show the plus charges here, right? Even though there should be a plus charge there, we just don't do it with metals. I know. If I took the phosphorus and pulled that off, what would I have? I would have PH3, the lone pair, right? This had a lone pair. Phosphorus is in the 5th row under nitrogen, so does that phosphorus have a negative charge? You've got three bonds, just 3 different phenols and a lone pair. So this is also a coordinating ligand, right? So it's not anionic. And then if I pull the last one off, right, our CO ligand, again, we'd have a negative charge on the carbon, but we'd also have a plus charge on the oxygen. So overall, this is just a coordinating ligand, but it's not oxidizing, right? So it has to overall have a negative charge. So even though it has a minus, it also has a plus, so that's a neutral ligand in total. Okay? So this rhodium has how many oxidizing ligands? So anionic ligands? 2. So it's going to be rhodium in what oxidation state? Rhodium 2, right? It has to be rhodium 2. So let's shrink that down a little bit. So now we know it's rhodium 2, right? 2 plus. So now we look at rhodium and see where rhodium's at in the periodic table. It's in the 1, 2, 3, 4, 5, 6, 7, 8, 9, 9th column. So rhodium 2 plus, normally rhodium has 9 valence electrons. 2 plus would have how many valence electrons? 7. Yep, 7 total. Yep, we're going to add these up. So the difference here is, right, separate out oxidation state from the type of ligand. So now we look at how many electrons is this donating? 6. 6 from that phenyl. That's 6. How many from the cyclopentadienyl? 6 as well. Right? So 6. Because of the lone pair, yep. It's coordinating to all these. So 2 pi bonds and the lone pair, right? So really this has an anionic interaction and then 2 dative interactions as well. Chlorine is donating how many electrons? 2. The oxygen from ethanol is donating 2. Right? So it still has that bond. So it's still giving up, still surrounding the rhodium with 2 electrons. It's not that it's giving them up, but it's the rhodium it's coordinating here. So it is still putting 2 electrons by that rhodium. The phosphorus, how many is that? That's 2. Carbon monoxide is also 2. So add all these up, what do we get? Some weird number. We get, let's see,
27.
is it 27? 12, 14, 16, 18, 20, 27.
Oh.
Right, 27. So that would be the electron count. Rhodium-2 with 27 electrons around it. Probably not a real complex, but there you go. All right, let's take a look at a special type of ligand with palladium, this allyl kind of ligand. So this is an interesting ligand because it takes up 2 sites. All right, it takes up 2 sites, but it's also anionic. Right, so if I pulled this off, right, well, this is showing us that essentially it's not necessarily meaning aromatic, but that this palladium is bonding to all 3 of these carbons with 4 electrons. So it's like 1, 2, 3 sites with 4 electrons. So if I pull this off, what that looks like is really this. So another way people draw this is they'll show a palladium bonded, and it's good with the other metals too, is like this. It means the same thing, right? This is, I would argue this is maybe a little clearer, right? This is showing the palladium bonding in an anionic sense to this carbon, and then in a dative sense to this carbon. So this ligand overall is oxidizing. It's anionic in one sense, and also a dative sense in the other. So it oxidizes the palladium, but then it also takes up, right, it's a 4 electron donor, and takes up 2 sites. That's the other big thing. My Aunt Jeannie's calling. Hope everything's okay. So the ligand can be bonded 2 ways. This is essentially called that. This is called that slipping part, essentially. So at this point, so that's basically the way it can look, right? Less clear, more clear. Let's kind of take advantage of this and see how we could use this in a more complicated sense for a Suzuki coupling. Let's say we were given a palladium-2 complex. So if you wanted to, if you saw this and wanted to redraw it like this, go for it. That's totally fine. Right? If you look at this and think, I don't understand that, draw it like that, that's totally okay. Right? They basically mean the same thing. So let's say we have palladium-2 with 2 of these ligands on them. Right? So this is palladium-2 because this carbon and this carbon are both, right, taking an electron from the metal. Right? So as we discussed up here, this would be palladium-1, right? There'd be a little 1 here. Right? Either way I draw it. So how can I convert this palladium-2 into palladium-0? So one way you could do that is, let's say there's an extra nucleophile outside. Let's say you have, I don't know. Let's say you have a lot of solvent around. Let's do methanol as a solvent. Now methanol is not a great nucleophile, but let's just say once in a while this could happen. It attacks that pi bond because the palladium has polarized it, right? Made it more delta plus. It's almost like an SN2 prime at this point. So what does this give us? This will highlight a couple things. It'll highlight a way to turn palladium-2 into palladium-0, but it'll also help us differentiate the difference between oxidation state and formal charge. Oxidation state is real, formal charge is made up. All right? So if I draw this, the palladium, did I do a reductive elimination at this point? No. So the palladium is still palladium-2. And this is still over here. Right? But did the palladium, who got electrons? So if I drew this out, if I said this was 1, 2, 3, there's now a pi bond between 2 and 3, right? And that oxygen is now bonded to 1. And there should be a plus charge where? Yep.
Was it the oxygen?
The oxygen, right? Think about who lost electrons, who's giving up electrons, right? The oxygen is giving up the electrons. So who gets the electrons in the end? So if this is a plus charge, who has to have the negative charge? What?
Carbon 1?
Carbon 1 can't have the negative charge, right? I brought electrons there,
And then you also.
pi bond moved up, and then what happened to these electrons in this bond? They went to palladium. So this is weird. So it's palladium 2 with a negative charge. Now, but be careful, it's okay. Right? You've seen stuff like this before. Just because there's a negative charge on the metal, where's the electron density really at? It's out on the ligands, or probably in this carbon palladium bond. So one thing we could do is say, well, let's just have this guy take those electrons, right? And see you later. Just leave. Now that's more like a reductive elimination. Now it's a formal reductive elimination, right? So think about it this way: the palladium got a lone pair, right? So it has a negative charge. It's still palladium 2. Once it loses this ligand, it's back to having those 2 electrons back, right? It was surrounded by 2 and 2, 4 total. Here it still has the 4 total. And then once it loses this, it goes back to palladium 0. Right? Because really, when it's bonded here, does palladium own any of these electrons? No. There's 2 electrons in a bond, right? But this carbon has both of them. This carbon has both of them, right? That's why it's oxidizing the palladium. Right? So both these carbons are taking electrons away. So here it got 1 pair, it got 2 back, and that's going to lose 2. So it's back to being neutral, back to 2, palladium 0. And you have the negative charge there. Now there's another way you could have done this. I'll show you another way you could do this. Right? And then of course this negative charge would take that H and would go there, right? The other way you could have done this is more like that BH4. Remember seeing BH4? Remember BH4 minus? So what if I redrew this as palladium with the minus charge, bonded there, and this other piece so then in one step, let's just have these 2 electrons just go get the H. Instead of having it formally ligand leave, why not just treat this like, remember we've done BH4? This is like, this carbon is electron rich, right? It's almost like a Grignard. That carbon's delta minus, even though the palladium has a negative charge. Have that go get the H, and then you're back to palladium 0 as well, because you're still palladium 2. But once that leaves, you're back to palladium 0. So there's a couple ways you could do it. Yes. Don't get too wishy. Don't get too concerned. I mean, this is a complicated example I'm showing here. But the biggest thing is keep track of your charge, right? Formal charge is different than oxidation state. Right? Keep track of your charges. Who got electrons here? The palladium did. So the palladium has a minus charge. But really, does the palladium have electron density? No. Its ligand does. So that really, it's like a carbon with a minus charge. Yeah, this could have gone this way too. It wouldn't have mattered either way. Okay, so now that I've shown you this super complicated way to make palladium 0, let's pretend I have palladium 0. And this is we're going to do this question that's it's 1D in chapter 6 in the Grossman. All right, 1D. So in that case, we have a cyclic compound with a polar bond to iodide, right? So we start with palladium 0, so I have that polar bond to iodide. Let's do an oxidative addition. So our palladium 0 now becomes palladium 2. So this is a Suzuki coupling. So while this was going on, we also have a boronic acid right, in the mix. And this is kind of plays in well to what we just talked about. Now, boron only has 3 valence electrons, so now it's only surrounded by 6, so it has an empty p orbital. So what happens here, we have a base in the system. It's sodium carbonate, so you can this is what I would do. I would just say base. Cheap. And I would say, oh, it's going to go to that p orbital. And what that's going to do, it's not going to kick anything out, but it's going to activate everything that's on the boron, right? So let's take a look at see what we just made. So we have the phenyl, boron. So we have an overall negative charge, right, to start off with. You see that base of the minus charge, right? So we have, right, so the base we actually have is Na2CO3. So you could draw that O minus, right? So instead of me drawing this, I just wrote base, right? And there's obviously Na pluses. So if this had a negative charge, who got electrons when I had this attack? Who got electrons? Boron got the electrons, right? So now boron has a negative charge, but wait a second. Is boron really what's electron rich? Who's electron rich? Everybody else, right? In particular, right, since we're in the business of making carbon-carbon bonds, we're more concerned about the carbon piece than the oxygens of the bases. So once this is activated, now this is more willing to do what with the palladium? Treat boron like a metal. What's it going to do with the palladium? Transmetallation, right? So what does that mean, right? So even though the negative charge is on the boron, the carbon of the phenyl ring is really what's electron rich, and at the same time the iodide will come back down. So that's that transmetallation. You're always trying to get the complicated stuff on the more expensive metal, usually palladium or rhodium. Right? Boron's easy. Boron's cheap. Right? So boron wants to bind to iodide, so it gets that off. But we need to activate the boron first, right? So now the phenyl's on there. You got your boron. We got to balance our charge. OH. Now it's bonded to iodine and of course base. Right. Now at this point, what do we want to do? Let's do some reductive elimination. Draw on our electrons. Electrons back to palladium. Make a new carbon-carbon bond. Perfect. Reductive elimination. So we end up with our final product. The phenyl, and we've regenerated our palladium 0. Got its lone pair back. Good. Sure, I'll do an example with O2. So what's O2 for, right? So obviously O2 is an oxidant. Now the problem is sometimes O2 isn't compatible, right? So a lot of times maybe we ended up with palladium 0, but our catalytic cycle started with palladium 2, right? Maybe palladium 2 was being like a Lewis acid, right? It was activating something. If there wasn't any carbon iodide, carbon triflate, or something like that, palladium 2 was maybe starting like a Lewis acid. But at the end of the day, we do something where we end up with palladium 0. That's not good because we need palladium 2 to make this work. So I have palladium 0, and I want palladium 2. Well, O2 will oxidize things, but sometimes these just aren't compatible. So you have to have an intermediary, and that usually is copper, 2. So essentially copper acts as this like electron shuttle almost. Like copper will gladly get oxidized by O2, and copper will gladly oxidize palladium. Or actually, you get reduced by, we'll find out. They'll get oxidized by that, and copper will work on palladium, right? So it's kind of as an intermediary. So let's say you have palladium 2. Let's just show how it works. So you have palladium 2, or palladium 0, and I want to get to palladium 2. if I put in 2 copper 2s, copper 2 will work on palladium and make it an oxidized palladium and add in, now it would be copper 1, right? So keeping track of our electrons here, right? What happened to our electrons? Well, palladium had 2. Copper 2 became 2 copper 2s became 2 copper 1, so 1 electron for each of the coppers, right? But now you'd say, okay, that's great, but only way this works is I need copper 2, but now I have copper 1. Well, copper 1 can get reoxidized into copper 2 by that O2. And usually there's some protons around, and you usually end up with 2 copper 2s again, and then maybe some water, right? Because O2 had to get reduced, right? If it's the oxidizing agent gets reduced. And then we got our copper 2 back, which can then work on our palladium again. So a lot of times O2 is a nice oxidant. The problem is it doesn't necessarily directly act on our metals. So sometimes we have to add in this co-catalyst, essentially. And we showed copper quite a bit. The interesting thing is copper works in 1 electron steps, right, where we've been using a lot of 2 electron steps, right? That's why we have to do 2 coppers, because it goes from copper 2 to copper 1.
And you can never go to copper 0?
You don't want it to go to copper 0, because then it's kind of a rock and might not be in solution anymore. Right, and there's ligands, right? And there's ligands on these things, right, to make sure they're soluble, right? One of the things ligands do is, right, make these metals soluble as well, right? Because you think about a metal, wouldn't be soluble in organic solvent necessarily, so ligands help solubilize these a little bit too, make them more organic-y. But yeah, usually it's 1 electron steps. You can go to copper 3. This is your classic table. What is it in the Gen Chem book, right? The redox potentials. Here it is, right? This is straight up redox potentials. So to kind of highlight that point of O2 copper 2 catalyst with a palladium 2 catalyst kind of motif, how this would work. So an example is 1H in chapter 6 in Grossman. So in this case, let's see, we have a long chain alkene. And let's see, we're in water and some H plus. All this junk is in here too. And the product we're going to make is essentially this whole thing. But we're adding a carbonyl. We're making a ketone. So we're taking this alkene and making a ketone, right? So everything else doesn't change over here. So really this is just frivolous stuff. Don't worry. This has nothing to do with anything. So what we're doing here, if this is 1 and 2, there's 1 and 2, I somehow need to turn carbon 2 into a ketone. Where right now, is there an H on carbon 2? There is an H on carbon 2. In the end, is there an H on carbon 2? No, so that carbon's technically getting oxidized, right? Of course it is. All of a sudden has oxygen bound to it. Where does that oxygen have to come from? That's the bigger question. Where does it have to come from? Well, what other sources of oxygen are there? I mean, O2 is a gas, and we've never seen O2 bind to O2 is relatively actually pretty inert. It's not going to bind to a metal, because we haven't looked at that kind of stuff. But there is water in the system, right? So I'm guessing that oxygen here is from water. That's where I guess it would come from. All right, so what's going to happen first? There are no really polar bonds, right? So I think the palladium is just going to serve as like a Lewis acid. So let's just have the palladium, right, 2 plus, right? So pretty electrophilic. Palladium with the chlorines, 2 plus. It's coordinating. So that's going to make that metal, that pi bond a little more polarized, right? Make it maybe a little more electrophilic. And so in this case, the water, which we know we want to bond to oxygen, carbon 2 anyways, will attack. It's almost like a ligand substitution. So I would call this a ligand substitution. Palladium's not changing oxidation states. I'm going to simplify this a little bit. So there's the palladium. palladium 2. There would be Cl minus floating around, right? I'm just going to call this R from now on. This whole thing is R. There's a oxygen on here, the plus charge. Let's do a little acid base. So let's see. We have our palladium 2. Our group, and now we have an OH, and we made HCl2. So far, so good? All right. So now what do we need to do? Well, we know we need to do what? I kind of said this at the beginning. Carbon 2 has a CH. Does carbon 2 still have a CH here? If this is still 1 and 2? I need to get rid of that H. What's the one way you guys know how to get rid of H's? Beta eliminations, right? Beta hydride elimination. This H is still there, right? Let's get rid of it, right? Alpha, beta from the metal. So let's do a beta hydride elimination. So a good old beta elim. So we still have palladium 2, right? Because beta elimination, does that change oxidation states? No. So what do we want to do here? Let's do reductive elimination. So that gets us to palladium 0, right? And we made HCl. So that palladium 0 needs to go back in and work the copper 2, right, which this is, right? This is, of course, copper 2. Is going to turn 2 of those copper 2s will turn that palladium 0 into palladium 2. Right? It's like the last slide, right? And then we'll have copper 1, which we need to turn back into copper 2. And O2 is going to turn copper 1 back into copper 2. Now this, of course, is what do we call this? What kind of functional group is this? It's an enol, and we need to tautomerize it, right? So HCl could help do this. I've drawn this a quick and dirty way before. To do it again, and that gets there. That's just a tautomer. Right? HCl could catalyze this. This probably doesn't happen within one molecule, right? But whatever. It gets to the product. Right? So this is that trick back again. Palladium 0, though, is not the active species, right? We started with palladium 2. So we need palladium 2 to make this work. So palladium 0 needs to turn back into palladium 2. The copper 2 helps it do that, which then becomes copper 1, which then needs the O2 to turn copper 1 back into copper 2 to help out the palladium 0. Round and round we go.